So this is phi for this point. This is phi for this point. This is phi for this point. Still less than pi, right? So we get here. It's still. I mean, what I'm trying to say is this, right? We measure angle from here. But finally, when we go like this, we should not measure it like this, but we should measure it this way. You see what I mean? So this is wrong, and this is right. This is phi. So you choose whichever is shorter, whichever is smaller, and that's going to always be between 0 and pi. So pi would be this. This is pi, which is points on the negative. Phi equals pi corresponds to points on the negative part of the z-axis. Did you have a question? Or no? Okay. All right. Now, what are these coordinates good for? Well, the first answer has already been given. In this coordinate system, it's much easier to describe the sphere. So the sphere is now given by the equation rho equals r. Instead of x squared plus y squared plus z squared equals r squared of the Cartesian coordinate system, or r squared plus z squared equals r squared of the cylindrical coordinates. It's just a simplest possible equation, rho equals a constant. So that's, in a way, justification for using the coordinate system and for the name. But that's not the only object which has a nice representation in this coordinate system. We can also represent a cone by the equation phi equals some fixed angle phi 0. So that's the cone, right? Let's look at this picture again. So let's suppose I fix some phi. I fix phi, and I look at all the points which have a given angle like this, phi 0, fixed to the z-axis. So then it's like this is the z-axis, and the point is like this. I don't know. I don't have enough visual aids, so I have to trust your imagination and your intuition. Maybe like this is better. I don't know. So the point is that this is the angle. So the angle is fixed. So it has to be the same angle between your points and the same z-axis. So the result is a cone. And because I don't specify what rho is, I don't specify the distance. It can go as far away as I want. So it's an infinite cone, kind of an upper cone going in infinity, right? So it's not bounded, unbounded cone. So don't think that I just drew one level curve for it, but it goes to infinity. So the cone is given by this formula, which is again much simpler than z equals square root of x squared plus y squared of the Cartesian coordinate system, or z equals r of the cylindrical coordinate system, which is not so bad, but this is better. This is easier to handle. So these are the things you should remember. The cone and the sphere have a very nice expression in terms of this coordinate system. Now, what about integration? What about integration in spherical coordinate system? So once again, we have to figure out what is the volume of the elementary object with respect to the spherical coordinate system. You see? So these are the elementary objects for the Cartesian and the cylindrical coordinate systems, which give us the usual formulas dx, dy, dz, and r, dr, d theta, dz. So now we have to do exactly the same for the spherical coordinate system. So what is the elementary object now? And again, by elementary object, I mean simply that you impose the condition that rho is between some rho 0 and rho 0 plus delta rho. And what was my second variable? Phi. Phi is between phi 0 and phi 0 plus delta phi. And theta is between some theta 0 and theta 0 plus delta theta. So let's draw this an object which corresponds to these inequalities. Like this. Like this, like this, like this. One like this. Well, this whole thing should be kind of dotted line. Okay, and like this and like this. Okay, you see what I mean? This. Well, in fact, this I can do it like this, so maybe it's better. So here, what happens here? First of all, this is delta phi, right? This is rho 0. So this thing is actually between two spheres. Imagine two spheres which are very close radii, very similar radii. So this is something which is between those spheres. And it's, first of all, we cut it by saying that the angle goes between, is confined within delta phi. And also, when we project this down onto the xy plane, this angle, I'm not going to draw it all the way, but the projection is going to be delta theta. So this is the projection onto xy plane. You see? So now I have to evaluate the volume of this, just like I have to evaluate the volume of this and of this in my other coordinate systems. So what is it like? What is this volume equal to? Well, we don't calculate exactly. We approximate it, and we approximate it by the volume of the cube. Sorry, not the cube, but a box. A box whose sides are given by the lengths of this kind of circular segments. They're going to be all circular segments. Okay. So this one is very easy to find. Well, first of all, this one is very easy to find. This is just delta rho. This is just delta rho. That's one side. Okay. Now this one is also easy to find. This is, you see, this is rho 0. And the angle here is delta phi. So this is rho times delta phi. It's similar to the way we found that to be r0 times delta theta. So it remains to find this one. Which I guess you cannot see this color, right? Oh, actually, it's better than the other one. It's kind of greenish. Can you see this one? Yeah? Oh, good. Okay. So this one is a tricky one because you would be tempted to take rho 0 times delta theta. But this is not correct. So this is only one, there's only one cell point here. The point is that this is the same as this. In other words, this actually is not. This is not part of a circle of radius rho 0 and confined within the angle delta theta. On the contrary, it is actually part of a circle on the xy plane. But the radius is not. The radius of that circle is this, which is not rho 0, but it is r. It is rho 0 times sine phi. So that's the only point that you have to realize to get the right answer. And then you've got delta theta. I'm trying to draw this like this. This is on the xy plane. And so this segment is actually, its length is rho 0 times sine phi delta theta. Okay? So the answer is, for the volume, it's approximated by rho 0 sine phi delta theta times delta rho times delta times rho 0 again. Oh, this is rho 0, really. And times delta phi. Yes? I'm trying to calculate the volume of this, right? And I'm approximating it by the volume of a box like this, which has the following sides. This side is rho 0 sine phi delta theta. That's this. Times delta rho, which is this side, times rho 0 times delta phi is the yellow side. So the end result is rho 0 squared sine phi times delta rho delta phi delta theta. Okay? So the upshot of this is that when you compute a triple integral in spherical coordinates, you have to introduce the factor rho squared times sine phi. Just a little bit more complicated than for cylindrical and polar coordinates. So the triple integral over some solid is rho phi theta rho times rho squared sine phi. Well, since I wrote it in red before, let me write it in red again. Rho squared sine phi. That's the factor to remember. D rho d phi d theta. Okay. So we do this calculation once and for all. Then we just memorize it. Rho squared times sine phi. And now after that, we can do the triple integrals by using iterated integrals for these three variables, rho, phi, and theta. Let's see how it works in practice. So here's an example. Compute the integral of x squared plus y squared plus z squared dv, where the region E is bounded by the xz plane and the spheres. X squared plus y squared plus z squared equals 9, and x squared plus y squared plus z squared equals 16. So between two spheres and also the xz plane. So first of all, I have to say, it's a general comment. Often I say on next week we'll have a midterm. On the midterm, I will not tell you which coordinate system to use. Right? You have to decide yourself. So the question is, you have to look for clues. Which coordinate system? Spherical, cylindrical. You have to remember one thing, that this expression, x squared plus y squared plus z squared, simplifies in the spherical coordinate system. So if you see x squared plus y squared plus z squared, how many times? 1, 2, 3 times. Chances are it's best to use, in this case, a spherical coordinate system. You see what I mean? Because this is rho squared, right? This is rho squared. If you see x squared plus y squared, that's r squared, r being the r of the polar or cylindrical coordinates. That's how you know that you probably should use polar coordinates or cylindrical coordinates, depending whether you are doing a two-dimensional double integral or three-dimensional triple integral. But in this case, it's fairly clear that you'd be better off using spherical coordinates. Now, we can try to visualize this. Think of a sphere, first of all. Let me draw just a quarter of this picture. Actually, yeah, about a quarter. So that's a part of the sphere. This is a sphere of radius 3 because 9 is 3 squared, right? And this is a sphere of radius 4 because 16 is 4 squared. So let's say this is a sphere of radius 3. And then this is the inner sphere. And then there is an outer sphere which has radius 4. So see, this one is inside the other. And what you're looking for is, what you want to look at is the three-dimensional shell, which is in between the two. In between these two spheres. It's like an annulus, but three-dimensional. Annulus is between two circles, and this is between two spheres. And also you have to bind, the other bound is xz plane. So this is the xz plane. So actually that's not the whole thing. This is one quarter of the whole thing. Because you will also have something in this quadrant and in those two quadrants which are behind the zy plane. So this is one quarter, so to speak, of the picture. But if I try to draw the whole picture, it will be more confusing. So you just have to draw the same thing, but 3 more times. And that's what you need to calculate. Now, actually here, the way it's raised, it sounds almost as though it's ambiguously defined. Because it doesn't say on which side of the xz plane. It could be on this, I draw it on this side, where y is positive. But it doesn't say that. So in principle, I could also look at the other half. But the point is that the answer doesn't depend on which half you choose. Because the function which you use, it does not change if you flip y, if you replace y by negative y. So if that were not the case, the problem would not be well defined, would not have been well defined. But actually it is well defined because the answer is the same no matter on which side of the xz plane you look. Okay? Now, to compute this, you write, see, this is one case, this is one coordinate system where you cannot so easily visualize the way I explained in the previous discussion for cylindrical and Cartesian coordinates, where I was talking about projection. Because these coordinates do not involve any of the variables of the Cartesian coordinate system. It does not involve x, does not involve y, does not involve z. So you have to be a little bit, use your imagination, and you have to just try to describe this by inequalities in the coordinates of the spherical coordinate system. So the inequalities will be in this case that rho is between 3 and 4. We know this, right? Then what about phi? Well, phi actually can be anything from 0 to pi. It takes the maximum range. And then you have to, the condition is on theta. if there was no condition about the xz plane, if the problem didn't say that one of the bounds was the zx plane, we would write that theta is between 0 and 2 pi, which is the maximum possible value, right? This is the total range of theta. But because we are bounded by xz plane, that means that theta can go from 0 to only up to here, but it cannot go further because we're on this side. You see what I mean? So that means that theta actually goes from 0 to pi, and that's what this extra bound gives you, right? So these are the ranges. And so actually, in the spherical coordinate system, this very complicated domain looks very simple, right? It looks like a box. It looks like a box. And so the integral that you get describing this triple integral is actually going to be the simplest possible triple integral with respect to this coordinate system. And you can choose any order you like for the integration because the bounds do not depend on other variables. You see, they're fixed. So it's like the basic integral. Yes? Very good question. Is it going to be like this for all problems for spherical coordinate system, or just for this one? Just for this one, of course, because you can imagine more complicated domains in which the bounds will depend on other variables, right? So I'm just giving the simplest possible example. Okay, so here you're going to have, say, rho from 3 to 4, and then phi from 0 to pi, and theta from 0 to pi, and then you don't forget your function, which is rho squared, and don't forget the extra factor, which is rho squared, this one, rho squared sine phi. So times rho squared sine phi, d theta d phi d rho squared sine phi. Huh? Sorry? Why is it rho squared times rho squared? It's called rho. So that's actually a good question on the midterm would be, what is this variable called? You know? And so if you write for p for this, then you get to that. It's quite deductive. So this is rho, right? Anyway, so this rho squared comes from the integrand, which is x squared plus y squared plus z squared, which is rho squared. And this rho squared comes from the extra factor. So the net effect is that you got rho to the fourth sine phi. So then you get a very simple manageable integral. Okay? I'm sorry? Hold on. There's one minute left. Yes, what again? Rho squared sine phi is always there, and then you have the function. Okay? So we'll continue Thursday.